So today's topic is the homogeneous linear equation with constant coefficients. So consider the nth order linear homogeneous differential equation a naught x y n plus a1 x y n minus 1 plus up to a n minus 1 x y prime and a n x y is equal to 0. So call this equation 4.23. Here a naught, a1, a2 up to an, the coefficients, these all are real constants. Okay, so though here it is written a naught x, a1 x, an minus 1 x, an x, all are functions of x, but here in this case all these are real constants. Now we have to solve this equation. So actually we have to find a function f having the, to find the function we have to find a function f such that if it and its various derivatives are each multiplied by certain constant. I am repeating, if it means the function f and its various derivatives are each multiplied by certain constants, the ai's, and the resulting product a, I, f, n minus I, because we have seen here when the suffix on a is 0, then the order of derivative of y is n minus 0, means n. When the suffix in a is 1, order of derivative here is n minus 1. So when suffix in a is I, the order derivative will be n minus I. So ai, fi, when all these are found and added, are then added, results 0. The result will be equal to 0. That means, in other words, I am searching for a function f satisfying this condition a naught fn, a1 fn minus 1 up to a n minus 1 f prime plus a n f is equal to 0 for all values of x for which this result is defined. For this to be the case, we need a function f such that its derivatives are constant multiplies of itself. So for this condition to hold, we need a function f such that its various order derivatives, say I am talking about kth order derivative of fx with respect to x, is equal to some constant multiplied by the function itself. Okay, and this is true for all x. Only then this condition will be satisfied. Now the question is that is there any such function which satisfies this condition? Is there any such function which satisfies this condition? Answer is yes, and the function is yes, we have such a function. Is there any function? My question is any function f satisfying this? Answer is yes. And the function is, such a function is fx equal to e to the power mx, where m is a constant. M is a constant. Okay. So here my question is that it is yes. Now if I find the kth order derivative of x e to the power mx, kth order derivative of e to the power mx with respect to x, then it is definitely m power k e to the power mx. And as m is a constant, m to the power k is also a constant, because k here is the order of derivative, order of differentiation. So we have a function which satisfies our requirement. Okay, thus we shall seek solution of 4.23 of the form. So we shall seek solution of 4.23 which is of the form y equal to e to the power mx, where the constant m will be chosen such that e to the power mx does satisfy the equation 4.23. So we assume that y equal to e to the power mx is a solution for certain m. We find the various order derivatives. The first order derivative, it is m e to the power mx. Second order derivative is m square e to the power mx. And the nth order derivative is m to the power n e to the power mx. Done? Now, if I put all these expressions in 4.23, so substituting in 4.23, 4.23 was a fn, and it's a naught multiplied by fn. So a naught remains a naught because it is a constant, but fn is yn, natural derivative of n. Yn is m power n e to the power mx. Then comes a1, yn minus 1, a1 multiplied by n minus 1 natural derivative of y. So it will be this, and the first order derivative is to be multiplied by an minus 1. First order derivative is m e to the power mx plus an multiplied by y, but y is here, e to the power mx equal to 0. And here we have seen that each term has a factor e to the power mx, or each term contains e to the power mx. So I can take it common. Then I shall get it not m to the power n plus dot 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 plus m a n minus 1 plus a n is equal to 0. But since, as we know that e to the power mx is non-zero for all x, for all real x, so we see that for all x, so we see that the product of these two expressions to be 0, we must have a naught m power n up to an minus 1 m plus a n must be 0. So call this equation 4.24. And here you see this is an equation which is actually a polynomial equation, because on the left hand side of this equation we have a polynomial in unknown m of degree m, n. So this is a polynomial equation in unknown m for mango, of degree n. Okay, and this equation is called auxiliary equation, or characteristic equation of 4.23. Okay, so if y equal to e to the power mx is a solution of 4.23, then we see that the constant m must satisfy equation 4.24. Thus, to solve equation 4.23, the original equation, we write the auxiliary equation 4.24 and solve it for m. Observe that 4.24 is formally obtained from 4.23, just merely replacing the kth derivative in 4.23 by m power k. Okay, because you just compare the two equations. Let me show the original equation 4.23. This is the original, no, this is not. This is the original equation, you see. So here in the first term we had y n, the nth order derivative of y. But in the auxiliary equation, we have seen in place of y n, we have m power n. In this equation, in the second term, we have y n minus 1, the n minus 1th order derivative of y. But in the auxiliary equation, we have m power n minus 1. And in the last term of this equation, on the left hand side of this equation 4.23, we have a n y. But in that equation, in the auxiliary equation, we have a n simply. Okay, we have simply n there. Then, so we can get the auxiliary equation just by replacing the kth order derivative in equation 4.23 just by m power k. So say it is simple. So depending on actually as this 4.24 is an equation which is a polynomial equation in m. So if I solve this equation, I will get at the most m roots. Now it may happen that all the m roots are real and distinct. So we can have three possible cases, three cases. So while I solve the auxiliary equation, we may face these three situations. So all the values of m are real and distinct. Second case may be m are real and equal. And last one, m are values of m are uh, distinct but complex. So we shall discuss all these three possible cases, and if m, the values of m are real and distinct, then what will be the solution, general solution of equation 4.23 that we see now. So consider case 1, distinct, real. Okay, so suppose the roots of so equation a naught m power n, a1 m power n minus 1 up to a n minus 1 m plus a n is equal to 0, which is the auxiliary equation. So suppose the roots of this are the n distinct numbers, say m1, m2, m3, mn. Then e to the power m1x, e to the power m2x, e to the power mnx are n distinct solutions. Because our assumption was y equal to e to the power mx is a solution of the equation 4.23, and accordingly we are getting the auxiliary equation 4.24, this one. So if we get n distinct roots of this equation, then the solutions will be e to the power m1x, e to the power m2x, e to the power mnx, and these all these will be distinct. Why? Because all those mi's are distinct. Now, by using Wronskian, we can easily verify that these solutions are linearly independent. Okay, these solutions are which are linearly independent. So, once you get n number of linearly independent solutions, you can easily find a general solution. So, what will be the general solution? General solution will be y equal to c1 e to the power m1x plus c2 e to the power m2x plus up to cn e to the power mnx, where c1, c2, c3, cn are arbitrary constants. So These things which we have found or which we have learned here are written in the form of a theorem, which is 4.11. Consider the nth order homogeneous linear differential equation given by 4.23, which has already been written, with constant coefficients. If the auxiliary equation (4.24) has n distinct real roots, say m1, m2, mn, then the general solution of 4.23 is of the form is e to the power m1x plus c2 e to the power m2x plus up to cn e to the power mx, where c1, c2, c3, cn are arbitrary constants. Then, so in the form of a theorem, we have got the result. So let us consider one example, not one, more than one example. Say example 4.20. So consider the differential equation. Y double prime minus 3y prime plus 2y is equal to 0, and we are to solve this equation. Call this equation 1. So what is the first step? Let us assume that y equal to e to the power mx be a solution of 1. Then if I differentiate both sides with respect to x, then I will get m e to the power mx. If I differentiate it again, then I will get y double prime equal to m square e to the power mx. So putting or substituting this in 1, we get m square e to the power mx minus 3m e to the power mx plus 2 e to the power mx equal to 0. And this will be giving m square minus 3m plus 2 is equal to 0. So what we have seen, the product of e to the power mx and m square minus 3m plus 2 is 0. And as we know that e to the power mx is non-zero for every x, so I could write x square minus 3m plus 2 is equal to 0 as e to the power, since e to the power mx is non-zero for all x. So I know what are the solutions of this equation. Solutions are m equal to 1 and 2. So call the first solution m1, it is 1, and m2 equal to 6, 2. So we have seen the two roots m1 and m2 are real and distinct. The roots are real and distinct. Thus, e to the power x and e to the power twice x are two distinct solutions of 1. And we can easily verify that these two solutions are linearly independent. How? Let us see how. Also, let us find the Wronskian of e to the power x and e to the power twice x. And it is e to the power x, e to the power twice x. Write their derivatives. And after multiplication, you will get e to the power 3x minus e to the power 3x, which is e to the power 3x only, and it is true for non-zero for all x. It is non-zero for all x. So what we can say, therefore e to the power x and e to the power twice x are linearly independent. Then, so we have got two linearly independent solutions of the equation 1. So to find their general solution, we have to write their linear combination. Thus, their general solution is therefore the general solution of 1 is y equal to c1 e to the power x plus c2 e to the power twice x, where c1 and c2 are arbitrary. Right? So consider more one example. Say example 4. Solve y triple prime minus 4y double prime plus y prime plus 6y is equal to 0. So call this equation 1. So as we have already learned how to get the auxiliary equation, so we shall immediately write the auxiliary equation from the given equation. So to get that, I have to replace various order derivatives of y by the corresponding power of m. So here third order derivative of y needs to be replaced by m cube. Okay. So we see that the auxiliary equation of 1 is m cube minus 4m square plus m plus 6 is equal to 0. And here we have seen that if I put m equal to minus 1, then it implies that left hand side is equal to 0. Minus 1 minus 4 minus 1. So total minus 6 plus 6, 0. So m plus 1 is a factor of the left hand side. So what we shall do, by synthetic division, we obtain the factorization. This m cube minus 4m square plus m plus 6 is equal to m plus 1 multiplied by m square minus 5m plus 6. But as we can factorize m square minus 5m plus 6, so we shall get it by splitting the middle term. Just by splitting the middle term, we can get these factors. So the auxiliary equation is, therefore we get m plus 1 into m minus 2 into m minus 3 is equal to 0. So values of m are minus 1, 2 and 3. So let us take m1 is equal to minus 1, m2 is 2 and m3 is 3. Then we have seen the roots are, thus the roots are real and distinct. Okay, and so the general solution is y c1 e to the power minus x plus c2 e to the power twice x plus c3 e to the power 3x, where c1, c2, c3 are arbitrary. So thank you everyone.